You might ask why differential equation, why we need it. One of the key ideas of key use of differential equations is modeling, to model to represent a real life problem in mathematical expression. Let me give you a few examples. We'll start with something that you're very familiar with. Now this one, let's say we have a particle. The displacement of particle is called the function s. If you differentiate this with respect to time, you get the velocity v. If you differentiate it one more time, that means dv dt. Of course, this would also mean d square x dt square will be your acceleration. All three of them are actually a form of differential equations, and we can use all three of them to represent the motion of a particle, whether it's a free fall like this, or a trajectory maybe, or even like a motion of a particle which is like this. Another practical use of differential equations would be in the field of economics, especially the basic theory of supply and demand. Will say we know P is the price of some things. Well, usually we call it goods, goods at a particular time. So the economics would say that for some constant, let's say A, B, is called them alpha and beta, that the demand of the goods would be something to do with P, is dependent on the price, and the demand, it will be the A minus B times the price. And supply of the goods is supposed to be could be represented as something like alpha plus beta times price. So very often economists would like to know how fast is the change of price in a particular period of time, and we can do this by using this to calculate. What they want to do is what's the rate of change of price with respect to time, and for ease of writing it, we sometimes write P prime T, and the definition of this is really the difference of demand functions and also the supply functions. And there is another some coefficients. The coefficients here, lambda here is supposed to be positive, and we don't really care about know about what those A, B, alpha, beta, lambda, but we just need to know the idea. There's a definitions by the economists, and this is actually differential equations. Now let me complete this, because I would like to show you what will you get, because if you write this out, this P prime T will be equivalent to, if you recall, this is lambda and P and S. The function P is really this, and the function S is really this one. So you end up seeing lambda, and you see A minus B P, because P is price and dependent on time, you can do this, and you minus lambda again, but this time you get substitute the S function, beta P. So really this P prime T equal to this on the right side, well, it is the differential equations which represents the rate of change, the speed at which a price changes. So this is another use of differential equations. The one more good example is modeling of growth of populations. In these examples is very specific examples of bacteria. You could think about population of lions, human beings, bees, and so on. But let's focus on this particular problem here. This is a simple form or simple version of a population model, but never mind, we work with this at the moment. And the information given is quite clear that the bacteria doubles every 30 minutes, and the model is actually given to you. And T is in minutes, and you're being asked to find what is P naught if after 2 hours population is given as follow. Well, so this is the functions here, or the model in a way, and here we know that 2 hours would be equivalent to, well, 120 minutes. So we are really trying to calculate this. P 120 is equal to P naught to the power of 120 divided by 30. That would be 4, I think, and it is equivalent to 1.6 10 to the power of 7. And if you do this working properly, you get P naught equivalent to this value. So that really means that the function of populations could be expressed as follows: is P naught to the power of t over 30, and we could just replace this power of 6 times 2 to the power of t over 30. So part B will be pretty straightforward now, because all we just need to do is substitute all these values. Of course, 3 hours means 180 minutes, and the answer will be as follow. The P 30 minutes will be equivalent to this. The P when 60 minutes will be this, and 3 hours is really 180 minutes, and that would be equivalent to this 1 times 10 to the power of 6, and this is 2 to the power of 180 divided by 30, and you should end up seeing power of 6 times 2 to the power of 6, and this really is 64. Just set the form this, or well, we can just say 6.4 10 to the power of 7 bacteria, of course. And finally, the part C is really something a skill that we need to acquire. I'm going to do just a small bit, start by a little bit, and then explain the way to do that, and give you the final answer to the coefficient of k. Well, you're going to start by starting by these functions actually given to you to the power of t over 30. Now, to differentiate this with respect to time, because this is what they really ask you to do, differentiate this, and also to find the value of a coefficient of k. It's very difficult to differentiate this directly. So what you're going to do is you're going to take ln both sides, and I will leave the heavy lifting to you. You have to do the rest of the work later, and it's an exercise for yourself, and you perform the differentiation, and this will be implicit for sure, and you should end up getting k. They'll be working here. K will be something of 1 over 30 and ln 2. So good luck trying this one.